Hello, students. Today we want to talk about limits at infinity. We're trying to complete the picture of limits, derivative, theory of the derivative, so that we have the complete analysis of functions. And when we go to plot a function or draw a reasonable graph of the function, we want to be able to add all of the detail that will give us an accurate depiction of the function. Now, if you recall, we've already talked about infinite limits, which determine vertical asymptotes. They're synonymous. That is, functions become unbounded when you have isolated zeros in the denominator. That, again, this is something we talked about early on and found that it to be very effective in understanding the unbounded behavior of functions. Even though we did not have a limit, a legitimate limit, we still were able to determine that the function would become positively infinite or negatively infinite as x would approach some real number from one side or both. So that was very important, the arithmetic. Now we spent time analyzing the derivative and how the derivative gives us wonderful information about extrema, information about shape, concavity, information about increasing, decreasing. So now we are adding all of the ideas that we were unable to do in our prerequisite courses. So let's get started by looking at the definition of a limit at infinity. I think you'll find this to be very intuitive and to basically support what you have done in your pre-calculus work. Now, the idea here is that when we studied infinite limits, we knew that the function was becoming unbounded by definition. And we looked through theory that supported that conclusion. Now what we want to do is let x pass to infinity and negative infinity. So what we will do is we'll fix a real number L, and we'll look at the limit as x passes to infinity of f of x equal L. That is, this is our hypothesis. What does that mean? Well, if you compare this to the original limit definition, we just had x approaching c. So the fact that x is passing to infinity will make a change in the definition, but it's a subtle one. So basically now we will take an epsilon positive, then there exists some number. Usually it's not specified that the number is anything but positive. It could be an integer, it could be a real number, it does not matter. There exists m positive such that if x exceeds m, then the function value f is within epsilon of L. So what is very useful about the limits at infinity is that this will be paralleled with our treatment of sequences in the following course. That is, with sequences, you are allowing the n, or the variable, to pass to infinity. So there is a direct relation between the limits of real valued functions and sequential limits. So we will gain much information about sequences as we work through this material. So again, we think of x being large enough so that the function is within epsilon of L. Now, if x is passing to negative infinity, we just look for instance, once we specify a positive epsilon, we say there exists a negative number, such that if x is less than said number, then f is within epsilon of L. So remember, before we would find a delta so that, for instance, x was within delta of c, that is, x was close enough to c so that f would be close to L, or within epsilon of L. So the change is basically with the infinity here. And of course, it's a major change, but it's not just a complete unraveling of the definition. It is just adjusted to reflect the fact that n is becoming positively infinite and negatively infinite. Now, there are many interesting rules that we get from this definition that we have been using in our prerequisite courses. And it is the following result here. Before I state this, let me just look at two very simple results that we use frequently in mathematics. That is, if we have the function 1 over x and we allow x to pass to infinity, then that limit is 0. And intuitively, what that would mean is that the numerator is fixed, the denominator is becoming arbitrarily large, or arbitrarily large in a negative sense, and the function itself, 1 over x, converges to 0 in the first case from above, and in the second case from below. And if you think about how we actually draw the function 1 over x, this is not a surprise at all. We've been drawing this function forever. That is, we think of the x-axis as being a horizontal asymptote. And of course, we have the vertical asymptote f of x, or excuse me, the vertical asymptote x equals 0 for the function f of x equal 1 over x. And so we kind of use this one as a standard parent function, which gives us much insight into rational functions. So again, what we want to do is to extend this concept to a power of x. And so now what we can do is require r to be a positive rational number. We are still dealing with rationals because our theory hasn't allowed us to let r be just any real number. But this is fine. We are very happy with this restriction. It's not going to pose any problems for us. And we'll let c be a real number. Now we want to extend these concepts. That is, now if we take the limit as x passes to infinity of c divided by x to the r, then we still get the 0 limit. And then as long as x to the r is actually defined for values of x less than 0, we get the same limit. So this is basically what we have been thinking about when we deal with rational functions, and I'm going to say a little bit more about that. But notice with this type of definition, again, we have the term horizontal asymptote. Horizontal asymptote. And we would always think, what happens as x passes to infinity? So here, what we're seeing is that as x passes to infinity, the limit is 0. As x passes to negative infinity, the limit is 0. So we say the horizontal asymptote is defined by the horizontal line y equals 0, or the x-axis, in a very similar way that we define vertical asymptotes. What we would say is that if the function becomes unbounded as x approaches 3, then we would define x equal 3 to be a vertical asymptote. In a similar way, we define y equals 0 to be a horizontal asymptote because the function limit in this case, as x passes to infinity and negative infinity, is 0. Now, one thing that's interesting about limits at infinity, if they are indeed limits, that is real numbers, then we can utilize the limit theorems that were not available to us when we were working with infinite limits. So the limit of the sum, the limit of the difference, the limit of the product, and the limit of the quotient, all of those results are valid as long as we have limits. And so that is really an extension to the sequential limit theorems that we will study in the next calculus course. So we do get more theory that is available to us with limits at infinity, and that I think makes the process a little bit simpler. Now, I will let you know that if you are interested, there are interesting proofs of both of these results that you can easily follow using the definition. And what I want to do now is to do an example where we determine a value of m, that is m or n, whichever you want to call it. So for instance, if we specify a particular value of epsilon, what m would suffice. Now, let's also remember, once an m or an n is selected, if you have a positive situation, certainly any larger m would work. If you have a negative situation, certainly any more negative number would work. Just like when we're thinking about deltas. Once we select a delta, any delta smaller will certainly work. So let's look at an example of this. I think this will help you to see how we can correlate the definition with a specific example, just like we did with the calculations at the beginning of the course. Here's the example. We have the limit as x approaches infinity. Let me move this up a little bit. Of 3x divided by the square root of x squared plus 4. It's up just a little bit. There we go. So we get a little bit more space here so that you can see the page. Now, what we're going to do is set epsilon equal to, in this case, 1/2. And in this case, we can, x is passing to infinity, so we use the letter m in that case. So determine an acceptable value of m. So remember, in order to do this, we first had to figure out what the limit was, and then we could work backwards with the definition. So that certainly has not changed. So first, let's go ahead and compute the limit using the fact that we have some nice algebra going on here. So we have x passing to infinity, and we have 3x. Of course, we'll be able to factor that 3. And then downstairs, we have x squared times 1 plus 4 over x squared. So we're just going to factor the x squared. Now, when you actually look at this, and we again remember the fact that the limit theorems are actually valid here, we can go ahead and factor the 3. And then, of course, the square root of the product is the product of square roots. So we have 3 limit as x approaches infinity, x. And then, of course, we have the square root of x squared. And then we have the square root. I'll write this with the 1/2 power since we've got the 4 over x squared. A little bit hard to squeeze all of that in. Just a little more convenient to write it this way. And now what we see in this particular case is we have x's that are positive. So just note that as you do your calculations, x is a positive number. Now, of course, the square root of x squared is defined to be the absolute value of x. And of course, in this case, that is just x. So now we have the limit 3 times the limit as x approaches infinity, x. And then we have x, 1 plus 4 over x squared to the 1/2. And of course, the x is absorbed. So now we have 3 limit as x approaches infinity of 1, and now we have the square root of 1 plus 4 over x squared. Now, at this point, you can use continuity. That is, by the quotient rule, we will see that the limit of 1 is 1, and then by continuity, we can run the limit into the radical. So this gives us 3 times, and of course, we've got the limit of the constant. I'll just write that as 1. and then downstairs. Now, of course, you can write fewer steps, but the first time you do this, it's good just to go ahead and write everything that you see as being valid. So now what we have is the fact that we've got a situation where we have a power in the denominator that's passing to infinity and a fixed numerator. So this term will be 0. And of course, the 1 is just 1. So we get 3 times 1 divided by the square root of 1 plus 0, which is 1. And that, of course, just gives us 3. So the limit in this case is 3. Now, the reason that we want to look at this particular example, this reminds us of rational functions. It's not exactly the same, but very similar. What we can see as x becomes large, the square root of x squared plus 4 basically behaves as the square root of x. And so we can also see that if we were to tend to negative infinity, we would get a limit of -3 in this case, because of course the absolute value of x would be the additive inverse of x. So what's interesting here is that we now can pass to a function that is the actual limiting function. So like what I said before, we'll say as x passes to infinity, we just say that the square root of x squared plus 4 is approximately the square root of x squared. And that's really what we're using in our algebra here, because we see this term passing to 0. So the key in all of this is the main result that we have with a fixed numerator and then a denominator that becomes infinite powers of x. And then, of course, you can now move this into rational functions where you look at the degrees of the polynomials in the numerator and denominator, and you can assign basic rules just like you did in your pre-calculus courses when you would sketch rational functions. So none of that has changed. We will continue to use all of that. We just now have an arithmetic basis for it. So what we can do, this is the limit. So now we want to work backwards. So consider the absolute value of f of x, which is in this case 3x divided by the square root of x squared plus 4 minus 3, which is the limit, and this needs to be less than 1/2. So we start with this, which is actually the conclusion of the limit definition, and work backwards to find an actual m that is acceptable. So let's just use the definition of the conjunction. So we have -1/2 less than 3x divided by the square root of x squared plus 4. And we'll just focus on the side of the inequality that will give us what we need. So we're going to need x to be bigger than some number, which will be specified by this inequality. So now, of course, we can add 3 to all of the sides here. So we have 3 plus the -1/2, which gives us 5/2. And we have 3x divided by the square root of x squared plus 4. And then, of course, we have 1/2 plus 3, which gives us 7/2. Now, what we want to do is focus on the part that will get us where we want to go, which is basically here. But notice we have positive numbers, and we know that the square function is actually increasing when we have numbers that are positive. So let's just go ahead and focus on this part here. So this implies, and we will square. Again, we have an increasing function because of the signs of the numbers. So we have 25/4 less than 9x squared divided by x squared plus 4. And now we can just cross multiply, if you will. So we'll have a, in this case, a 36x squared. Now what's interesting about all of this, and when you think about it, it's not that we are trying to manipulate what we have. We're simply trying to do this in a way that evolves a number that will work. And so whatever number that you come up with, as long as you get it legitimately, you will be fine. So let's go ahead and cross multiply. So we get a 36x squared. And then we have greater than, and of course, this will give us a 25x squared. And then, of course, we get a 100, 4 times 25. And now if we subtract, we just have an 11x squared should be greater than 100. Now, at this point, we are interested in values of x. For instance, right now we've got an inequality, but we want to focus on values of x that are actually positive. So if you think of this, we could say equivalently, x squared is greater than 100 divided by 11. So if you look at this and you take square roots, then you have what we call a disjunction, okay? But we're only interested when x, for the values or the absolute value of x being positive. So this will imply, focusing on the principal square root, x is greater than the square root of 100 divided by the square root of 11, which is 10 over the square root of 11. Now, of course, if we were passing to the negative infinity, then we would be focusing more here, and then we would look for the values in the disjunction that would place us into the negative values. So here, what we're doing is specifying the values of x that will work for our particular problem. So now what you see, we can set this to be a value for m, and any x bigger than 10 divided by the square root of 11, all of this can be backtracked, will imply that the function is within 1/2 of 3. So again, as long as we apply mathematics that is correct to the procedure, then we can specify the value of m. And of course, in this particular case, any value bigger than this would also work. So we will write this down, set m equal to 10 divided by the square root of 11. And that will be an acceptable value of m for the definition. So again, we see the use of so much of the inequalities that we have worked with. And the beauty of all of this, again, if we think about this, and this is very important, if we just look here at this particular example here, notice if we did this in complete detail, we'd have the absolute value of x is greater than 10 divided by the square root of 11. And we've only focused on the values of x that are positive, because this would imply that x is greater than 10 divided by the square root of 11, or x is less than the additive inverse of 10 divided by the square root of 11. So equivalently here, we have x greater than 10 divided by the square root of 11, and I'll put this down here, or x less than the additive inverse of 10 divided by the square root of 11. So that gives us kind of the full picture here, but we're not interested in this one. We're only interested in this. So as we move from here to here, we're simply focusing on the values of x that are germane to the actual problem here. So we're not neglecting the algebra because we don't think it's important. It is important, but it's not going to help us in this particular example. But feel free to write down the complete story if you will. But I simply am focusing on the values of X that will work. So this gives you an idea. Basically, that was just like the procedure that we used with the epsilons and deltas at the beginning of the course. Okay, now I want to say a couple of things about the limit theorems. As I've said before, we get a very nice slate of theorems that we used with the standard limits at the beginning of the course. That is, we have the sum and difference rule, we have the product rule and the quotient rule, which we have already used. Now, the main thing is that I have given you some arguments about proving 3, the quotient rule, and also I provided the details and the estimations that you can use to do that. This is a very, very important example, at least in that it sheds light on sequential limits. So what I would recommend is that you actually look at this once you've had a chance to work with some of the actual examples and come back and check the very simple estimations that we use here. And they are simple. They simply get the job done, as they say. Students will always ask me, why do we do this? And I'll say, well, the main thing, it gets us further on in the problem. It moves the process forward, and it's an effective tool. And so it doesn't mean that everything we do is just smoke and mirrors, but there will certainly be techniques that will be useful to us. Now, I also want to make a comment about your time in your pre-calculus course and your college algebra course. We have conventions with infinity, which we have dealt with, especially when it comes to doing inequalities. Those are not new. But I want to just mention what we have been doing when we thought about the limits of rational functions. That is, the rational function by definition, ladies and gentlemen, is a ratio of polynomials. And so this was a very useful construction when you were asked to sketch graphs. So you would identify horizontal asymptotes, you would identify vertical asymptotes, and then, of course, in cases, if you had a slant asymptote where the degree of the numerator was 1 more than that of the denominator, or even a quadratic asymptote, whatever, the function was then going to infinity. So I just want to remind you that these can actually be proven using the factorization method that we used in the last problem, just to isolate all of the terms that go to 0, and then, of course, the terms that survive, so to speak. So the rules that you had before are still in force because they are supported by the arithmetic of the limit definition. So if the degree of f were less than the degree of g, and x was passing to infinity or even negative infinity, we would get the horizontal asymptote of 0. And then one of the favorites, I think, of the students was when we had the degree of the numerator equal to the degree of the denominator. That would be an indication of checking the leading coefficients. Now, what's interesting here, and this is very important, when the degrees are the same, the largest powers of x, as they're factored, absorb. And then you're left with other terms, aside from the leading coefficients, that all go to 0 because they have powers of x in their denominator with fixed numerators. So it is sufficient to find the horizontal asymptote by looking at the ratio of the leading coefficients. And of course, that takes into account the signs that may be associated with the leading coefficient of the numerator and the leading coefficient of the denominator. That's taken care of. Now, I have an example here where we consider the fact that the degree of the numerator is greater than the degree of the denominator. So we have to be a little bit more careful. Notice when you factor, you can factor the degree of the denominator or that power out, but then, of course, you'll be left with a power of x, which is raised to the n minus m power. Okay, so that must be taken into account when we are configuring a problem as x passing to infinity or negative infinity, because that will impact the sign. So what's important here is that not only do we look at the leading coefficients of the numerator and the denominator, but we also have the residue, so to speak, of the power of x that survives. All of that needs to be taken into account. Clearly, we will get infinity because the degree of the numerator exceeds that of the denominator, just like working with any polynomial. And so we were able to assign the correct plus or minus to infinity by not only looking at the leading coefficients, but also the residue power of x. And again, if x is passing to infinity, then the value is positive. You can just put in a positive value, think of it that way. X is passing to negative infinity, then you have to consider the power that's the residue power that's left. If it's positive, it will absorb. If it's odd, it will survive. So this is very important when you're considering the case where the degree of the numerator exceeds that of the denominator. So all of this was in play in your pre-calculus techniques. There wasn't as much arithmetic support for that, but it certainly had an intuitive appeal. So what I want to do now are some further examples. I think you're going to find that the limits at infinity might be a little bit easier than the infinite limits. Maybe in as much as you've had more experience with them, maybe thinking about the rational functions, but the algebra may be a little bit longer in the sense that once you figure out, a vertical asymptote, you're just doing a sign test. That can be tricky if you don't pay attention to what you're doing. But so what we want to do with the limits at infinity is make sure that we are abiding by all of the definitions and the limit theorems that we have. So let's look at a few examples of this. And I think you'll find that many of them are just like what you thought they would be. Let's look at a very simple example. So we have the limit as x passes to negative infinity of 4x minus x over 6. Now, when you look at this, you're thinking, well, this is not really what I expected, 4x minus x over 6, because you look at this and say, well, that this term would actually approach 0 because we have 4 divided by x and x is passing to negative infinity. And then here you're thinking this particular term will become infinite. So maybe a better way to address this problem is just to look at it in terms of the rational function by getting a common denominator. Again, you might be thinking, well, you can just pretty much break this up, but you really can't do that because you've got the infinity resulting here. And so that's not a standard limit. So those don't really apply. So let's dress this in the version of a rational function as we just discussed. So we can have a little bit better way to interpret this that looks more algebraically correct. So we'll just get a common denominator, which is 6x. And then now, of course, this will give us what we need, have a negative x squared. And then what, plus a what, 24? So now 24 over 6x will give us the 4 over x. And of course, the negative x squared over 6x will give us the negative x over 6. And now we've dressed this as a rational function, the ratio of two polynomials. So now let's go ahead and factor like we did in the previous. Now what we see is that the degree of the numerator is bigger than that of the denominator. So this will give us, let's factor the x's. So we have the limit as x approaches negative infinity. So we have x and we have x, and then we're left with negative x plus 24 over x. And then downstairs, we just have a 6. So these absorb. So we're left with the limit as x approaches negative infinity of, in this case, we have negative x plus 24 over x divided by 6. And so now we can just look at the leading term, so to speak, and attach the sign to infinity. Now notice x is less than 0. X is less than 0. That's very important. So this gives us the sign of negative x over 6. Now, of course, let's go ahead and write that with the residue power so it looks right. Might as well. So we have the -1, we have the 6, and then we have the residue power, which is just x. That's the n minus m. And then, of course, if we replace, and of course, this is an infinity that we're attaching the sign to. If we replace x with a negative number, then, of course, the negatives absorb, and we just get positive infinity. Now, you could look at this and say, well, if x is approaching negative infinity, arithmetically, that switches to a positive, and that would be kind of a quick way of getting to an answer. But we haven't really addressed the process. You're thinking that's kind of like doing infinite limits in a way, where we have infinity plus a number that is finite, so to speak, but it's not really the same thing, because this is approaching 0 when we think about it. And so we have to basically look at this as the ratio of two polynomials to actually do it based upon the theory that was set up. So again, if you're about to run out of time, you can always look for a quicker way to do things. But we want to think about, like I said, this particular result here, which we can prove rigorously about the limits of rational expressions, which you did in an intuitive manner in your pre-calculus class and also your college algebra class. So this is kind of neat that we're seeing that all of these items had to do with the calculus, that is the computation of limits. And we really see that the heart of mathematics is tied up in the calculus, whereas when we decide to take the calculus, we use every math that we've ever learned: geometry, algebra, number theory, combinatorics. Everything is mixed into the study of the calculus. Now, one thing that I think will be interesting, I like the functions that have the square roots in them, because they give us extra practice. And then, of course, if you have a difference in a particular problem where you have, for instance, like an infinity minus an infinity, which is indeterminate, you can use a conjugate method. There's an example in your homework that will allow you to use a conjugate method, and it's written up in the lecture notes, that I think you'll find to be very effective. It should remind you of some of the calculations you've done with derivatives, and it's very straightforward. But that will also be a technique that will be available to you when you have to deal with certain forms that don't present very well. Of course, we can't say infinity minus infinity is 0. That makes no sense. Infinity is not a number. So we have to adjust the algebra to provide more information about what's going on with the function. So the last example I want to do is this one. We have the limit, in this case, as x approaches infinity, of the square root of x squared minus 6 divided by 4x minus 4. So again, we're back to a simple example in the sense that it mimics the first one, but except now the radical is upstairs instead of downstairs. And so we're thinking the numerator is basically acting like what? The absolute value of x, because the x squared minus 6 is essentially x squared as x becomes infinitely large. And so then we're thinking, okay, we're going to get to a factoring setup again. And then, of course, if x were passing to negative infinity, we'd have a similar situation that we had in the first problem. So this really opens the door to some algebraic manifestations, which adds a little adjustment to these problems with the rational functions. So just like you work with trigonometric functions and algebraic functions, they mimic the ideas that you utilize with the rational functions. And those are supply us with a very rich arithmetic, as we see in the previous problem that we did. So let's do this one. So we have the limit as x approaches infinity, and we'll do the factorization again, x squared times 1 minus 6 over x squared to the 1/2. And downstairs, if you like, we can just go ahead and, what do we have? We can factor an x. So we have x, and we have 4 minus 4 over x, if you like. We'll just start out with the x's. And this will give us the limit as x approaches infinity. And now, of course, the square root of the product will give us the square root of x squared, and then the square root of 1 minus 6 over x squared to the 1/2 power. And then, of course, we have the x times the 4 minus 4 over x. Now, of course, this will give us the absolute value of x by definition. And now, of course, x is positive by the given problem. So we can replace the absolute value of x with just x. Let me give a little better symbol to the infinity. And so we've got, in this case, x 1 minus 6 over x squared to the 1/2. And then, if you like, the x downstairs absorbs, and we've got, well, let's go ahead and factor the 1/4 if you like. We can factor that, and then we just have 1 minus 1 over x. So these absorb. So this gives us 1/4 times the limit. Now, of course, we can go ahead and run the limit upstairs. We'll do that and just go ahead and run that using continuity. 1 minus 6 over x squared to the 1/2. And then downstairs, we just have the limit of 1 minus 1 over x. So, of course, this will give us 1/4. And then we have, in this case, the square root. Of course, this term will tend to 0. So we have the square root of 1. And then, of course, here, this term tends to 0 divided by 1. So we just get 1/4. So when we look at these types of calculations, the process of determining an m or n, as the case may be, is very similar to determining a delta. So not difficult. Again, you work backwards. And so that's why I wanted to go over that example. And then the rest of the theory basically relies upon the fact that these terms of this nature go to 0 as x passes to infinity or positive infinity. That is really the linchpin that makes all of the examples here rules work with the rational functions that we so depend on. Okay, so now when we have limits at infinity, we're now defining horizontal asymptotes. So when we look at this function here, we say a horizontal asymptote is now defined to be y equal 1/4. So like I said before, we would tend to make a big deal about infinity when we would have a oblique or slant asymptote or quadratic asymptote. That really maybe lends a little bit of help to sketching the function, which is fine. But again, the function is becoming infinite. The more interesting cases we find is when we have the horizontal asymptote y equals 0, where the degree of the numerator is less than that of the denominator, and then when they're equal. But of course, the whole idea behind the limit at infinity is that it does possess some theory that is very similar to the theory of our original treatment of limits. And so we can at least rest assured that as we move to the theory of sequences, we could drag along a lot of that theory. And of course, if we simply restrict the values of x to integers or natural numbers, we can drag the limits along too. So there's a very beautiful attachment of limits at infinity to the theory of sequences. So that's something that we'll look forward to doing in the next calculus course. So I think you will enjoy the infinite limits. And then, of course, when we talk some about more curve sketching problems, we'll be able to put that part of the picture to rest. That is, we have the asymptotes, we have the extrema, we have the shape with concavity, the intercepts, all of those ideas, sign test. What we're seeing is that all the sign tests that we have developed in the prerequisite courses are really the mathematics of calculus, because everything really turns out to be a sign. You know, we have approach, you know, what are the values of x in this case? How do we interpret the absolute value? So we're finding that the arithmetic of calculus is actually what we've been doing in the prerequisites. So enjoy doing these types of problems, and also think about some of the examples that you did in your pre-calculus classes in college algebra and compare. Go back and look at those and just refresh your memory as to what you knew at that time. And now that you have the additional information, you can actually now write the complete picture. But let's just also be interested in the fact that in many cases, we know we didn't have any extrema. I mean, the problems didn't allow for it. And now we know that that is indeed the case using the arithmetic of the calculus. So that's all I have to say about this. I'll see you soon.